So welcome everyone. So it's my pleasure to welcome Wei Kang, who will be talking about data-driven computational methods for the domain of attraction and Zubovs equation. Thank you.
Okay, thank you, Boumediene, for your invitation. It's always a pleasure to talk something, give seminar in Turing Institute. Okay, also start your video. So start my video. Okay, is that whatever? Yeah. So and also thank you for coming. I know that it's kind of late in UK time, so I'll keep that in mind. Hopefully, I don't use too much of time. It's not a particularly long talk anyway. So we'll talk about data-driven computation methods for the domain of attraction and the Zubovs equation. And most of the part, most topics and results talk about today is joint work with Kai-Shun and Liang Xu, and Kai is a professor at the University of Tennessee, Knoxville. I've been collaborating with him for a long time, for more than 10 years. And Liang is from a Naval Research Lab in Monterey. And also, I've been working with group of people from groups of people from different places on machine learning related topics. Okay. Anyway, but these days I like to start from the cursive dimensionality. Okay, so that every talk I gave, I spent a couple of minutes about cursive dimensionality before I go to the subject, because for many years my work is related to this topic. So cursive dimensionality. Let's talk about function and approximation. You can use. By the way, this is a picture of Lyapunov. We're going to talk about Lyapunov function today. So I found a picture online of him. Say you have input-output relation between I mean that's a function basically. It's the input-output relation. It can represent a model of a system, or can represent a feedback controller or feedback control law, or it can represent the Lyapunov function that gives you stability. Whatever it is, it's an input-output relationship. We'll try to approximate that, right? So then you can do it in different ways. In machine learning, we often call it regression. You'll find a neural network that approximates function, but actually this is a problem has been studied in numerical computation for forever, right? So you can do interpolation. If you know the value of the function at certain sample points, you can do interpolation, or you can, if you can project it to the orthogonal basis, then you can do spectral method. So this is a problem has been everywhere in engineering and mathematics. It has been studied using many different tools. Then the question is that what's a big deal? Why I still want to talk about? Then that's the big deal here is actually is a dimension. When you approximate something, or you try to represent something as an input-output information relation, you have these three factors to consider, right? Suppose the approximation error is bounded. Let's say you want to guarantee a certain bound of error. Then these two factors start to interact with each other. The dimension of the problem, or the input dimension, it's the input dimension of the function, will impact the complexity of your solution. Whatever the complexity mean, you may have different definition of complexity, but when you increase dimension, the complexity of your solution or your approximation solution will increase. Okay, now here is the challenge, the so-called cursive dimensionality. That's a phenomenon in which if you fix your error of a bound, then the complexity of your solution increases exponentially with the dimension, and that's a cursive dimensionality, or COD, is a term coined by Richard Bellman. He actually gave this name, which represent a typical phenomenon in many of these problems of regression or approximation. So now what do you mean by complexity? Now let me put it in perspective. Let's put this cursive dimensionality in perspective. For example, you use the memory data size to represent the complexity. If that's the case, then exponential increase is that there is a base number, then the d is the dimension of the input of the function. Then when d increase, you see that the increase, this variable is in the power. So that means this n to the d is a total size you need for memory or whatever the data you need, and that increases exponentially. But everyone knows that n to the d increase very fast, exponential is very fast. But actually, I still want to put it in perspective. How fast is it, right? So let's use interpolation as example. You use the spectral or pseudo-spectral approximation similar. Say you want to approximate a function, two-dimensional input, okay, x and y, all right? And then you know the value of the function at the grid points, all right? Then you need to remember, store this value in your computer. That if you have x and y somewhere in between the grid point, then you can actually approximate the value of the function using the grid point value that you know, and using interpolation, do interpolation, right? So so how much memory you need to memorize the solution, and especially when dimension increases, here is the result. Basically, let's assume that in each dimension you have 50 grid points. So it's not particularly high accurate, okay? So you have 50 points in each dimension. Then suppose you only use a single precision. Then the memory you need versus the dimensions like this. So if you are 4 or 5, you need a gigabyte of if dimension 4 or 5, you need about gigabytes of memory. Okay, if you go to 6 or 7, you need a terabyte already. Okay, 8 or 9, you need a petabyte, and 10 dimension you need e-byte and whatever byte. You see that how fast. And now, of course, I'm not talking about hard drive memory. Although you have terabyte hard drive memory, I'm talking about the memory you need to upload to your CPU and do computation, right? So once you go to beyond gigabyte, that's something, a few gigabytes fine, but not only the memory in CPU, you have to, worry about the bus traffic, right? And when you get to terabyte, just no way you can handle that interpolation problem, right? So basically here from the graph, it's clear that if you use conventional approximation method, like interpolation or even a spectral method, they actually, once you go beyond 4 or 5 dimensions, things become impossible. Okay, unless the problem has special structure or the problem can be, in some way simplified. Otherwise, brute force approximation does not work. So that that is the situation of cursive dimensionality. Okay, so today we're going to talk about how to approximate the optimal function. So that is, if you don't do things right, it suffers the cursive dimensionality. All right. So, but anyway, let's go to the domain of traction and the optimal function, stability, stuff like that. Okay. So suppose you have a ODE, all right, and then you have a set of invariant set. This invariant set, so the stability here is not necessarily a single equilibrium point. The invariant set can be a set of equilibrium points, or can be even a periodic trajectory. And so anyway, it's an invariant set. And then the invariant set is asymptotic stable. Then the question is that, how can you find the domain of traction, or how can you characterize the domain of traction? In high dimension, you cannot draw the graph, right? So you need an effective way to characterize how close you are to the boundary of domain traction, right? So that's the question. That's, of course, we know that this question is closely related to the optimal function, because if you have the optimal function for a system, then its level set, enclose invariant subset of a domain abstraction. So so the optimal function can at least tell you the subsets of invariant subset of the domain abstraction. Although most of the optimal function do not give you the boundary of the domain abstraction. Okay, then this is a huge, literature. There's a huge literature. Okay, there's no way, I just list a few of them, and I have to admit that I don't know all of them. Okay, it's huge. There are just so many different ways to find the optimal function, and so on. So a lot of those are based on Zubovs equation, which I will talk about today also. And then there are other ways, using LMI, or if the model has kind of back triangular type of structure in optimal control, or in control stabilization control, then you can use backstepping. And then people use sum of squares. And then I know that Giso and Boumediene actually had some work on using radial basis functions. I highlight this one. It's a Lars Boone, so using deep learning, because it shares some similar, similar ideas that I'm going to do today. In the sense that I also use one of the methods I propose here is a deep learning. But the difference in Lars' work, this is also fairly recent work. In Lars' work, he actually used. I think his training is more like a PIN, physics informed learning. That's my understanding. In the sense, it's similar, because the loss function in the training integrate the Zubovs equation into it, and also he assumed that the family of system he deal with satisfy so-called small gain assumption. So in my case, I use supervised learning, and also I do not assume small gain for the system, but the designs heavily based on the assumption that the function has compositional structure, which I think is quite general in engineering systems, which I will talk more. But anyway, so I think this is very interesting work. This is very interesting to me. It's very interesting, so I highlight it. So then, if you look at these papers, these different approaches, I think that I summarize the challenges in the three different types of challenges related to this problem. One is that some design methods need special type of mathematical model. As I mentioned, it's maybe a triangular structure you need. The model to have something like that in the algebra representation, or you maybe need a polynomial representation or whatever, right? So some method requires special type of mathematical model, and then some work can work only for low dimension. Once you push it beyond 4 or 5 dimension, that becomes impossible. And then also another big problem is that you often find the optimal function, it gives you the invariant subset, but if you are outside that subset, you don't know it's in the domain abstraction or not. Or in other words, you find subset of DOA, but cannot characterize the boundary of domain abstraction. That's another challenge. So I would say, most of the existing methods, they actually probably can resolve 1 or 2 of these challenges, but not all 3 collectively, and that's tough. I mean, to solve all the 3, you want everything. You want to find the domain abstraction's boundary. You want to work in high dimension. You want to to work for general any control system, dynamic system. So that's hard, right? That's extremely hard. I'm not saying that I'm going to solve this. However, I try to face these challenges all together collectively. Although I still need some assumptions, and then but I try to, at least the effort is trying to say, can we find a solution to Zubovs equation, which gives you the optimal function for relatively general nonlinear systems, and can you not overcome, at least mitigate the cursive dimensionality. Try some problems with 5, 10, even 20 dimension. That's using brute force approximation conventional method is impossible, right? Can you try some of those, relatively high dimension, and also not only subset? Can you tell me where is the boundary of domain abstraction? Can you characterize the boundary of domain abstraction? So I'm trying to kind of face all the three challenges together collectively when I try to solve the problem of Zubovs equation and the domain abstraction. Okay, so I'm going to propose two related but different approaches. One is a inequal form of solution, which is a part of it is based on data. So it's a kind of data-driven inequal form solution to answer these questions together. But this one does not answer the cursive dimensionality. Okay, so if you have high dimension, then I propose deep learning. Okay, so that's what I'm going to talk about or trying to introduce. So this is a Zubov. He has a book actually. So there are the so-called Zubovs theorem. There are different versions of that. So I use one of these theorem from his book. Then he made some assumptions there. Now keep in mind your invariant set of stability may not be bounded. Some of these assumptions, if the invariant set, so this kind of capital E represent the invariant set. So this invariant set, if it's bounded, then maybe some of the assumption is not a big deal, and then but it's more general. So this is invariant set. It may not be bounded. It can be a single equilibrium, or can be a set of equilibrium points, and it can be something like a periodic solution, or maybe multiple periodic solutions. But anyway, it is invariant set. It's a asymptotic stable, and then it is assumed. Zubov assumes that so a domain of attraction is a capital D. Assume it's uniformly asymptotic stable in the neighborhood of the invariant set, and then also it is uniformly attracting. That means if you are h distance away from your set invariant set or stable invariant set, then in a finite time interval, you are at least gamma distance away uniformly. So that's a uniform attracting. So actually the assumption I made, I will make in this presentation will guarantee this too. So you don't have to worry too much about that. But anyway, so based on this assumption, then Lyapunov proved, Zubov proved this theorem that is a special V is a solution of so-called Zubovs equation, look like this. And so the derivative in the direction of the dynamic system equals to another function, positive definite function, times 1 minus V. So now this solution V is a special type of Lyapunov function. Why it's a special? Because it's not only it's between 0 and 1. Okay, everything here is positive definite and equal to 0 in this stable environment set. Not only they're positive definite, the interesting part is that you give me any point on the boundary of domain abstraction. D is the domain abstraction. On the boundary, there's a V function approach to 1. So that characterizes the domain abstraction. Okay, so once you get closer and closer to 1, you know that you are getting very close to the boundary of domain abstraction. Small perturbation may drive the system outside the domain abstraction. Okay, then it becomes unstable, right? So that's a special type of the Lyapunov function, and this is this basically you can write this into the form of PDE, partial differential equation, because that's direction in the direction of the ODE. But this one has infinite many solutions, and so it's not easy to solve. But anyway, so that is the Zubovs theory. Now, here, how to, as I said, I propose two different solutions. So that, I propose two different solutions. Let's start from this integral form solution, how to solve this one. Here, I need a few assumptions. I think they are not too bad. These assumptions are not too tight. For example, I'll assume that your x dot is f of x is the right hand side of your ODE. So when I say dynamic system today, I mean ordinary differential equation in Rn. Okay, so f is a local Lipschitz, and f is bounded in a neighborhood of the invariant set, the stable invariant set, and then this trajectory is defined from 0 to infinity. Okay, so actually I assume that one. And then also I assume we often use a function called W. It's a positive definite function, and it equal to 0 in this invariant set. And also I want this to be bounded below if you are distant, delta distance, any delta distance away from the stable invariant set. So that's a so for example, if you define W is x squared, right, or the square of the two norm, then it satisfies all. If you know the equilibrium point, there's the equilibrium point. So that's one obvious example, right? So so these assumptions are not too hard to find. And then also now this one, when you take a look at this assumption, it doesn't look obvious. But anyway, well, I assume that this W function, if you do integration along its trajectory in the neighborhood of the asymptotic stable, in the neighborhood of the domain of the attracting invariant set, its limit. I mean, it converges, and also more importantly, when x getting closer and closer to this invariant set, this integration approach to 0. Well, this one in general, you may need to verify that. However, most of the cases, I would say, in engineering, you get uniform exponential stable. If that's the case, even this E, the invariant set is unbounded, you can still guarantee this assumption. So basically, for the example I show you will be exponentially convergent. So this actually assumption is actually satisfied, but in general, you need to verify that. Okay, so that's some assumptions. Then here is the solution. I call it integral form solution, because I keep in mind this. I define this integration right along the trajectory, and suppose you have a positive definite function satisfy the assumption, and then you define this integration times some constant. I'll talk about the constant later, and take hyperbolic tangent if this integration is less than infinity, and otherwise it's 1. And then you define psi in this way. Then you solve the Zubovs equation in the sense that it satisfy. I can prove it satisfies this Zubovs equation, and also satisfy all these conditions. So this is the function that claimed in Zubovs theorem. So it has a relatively explicit form, except that you have to numerically compute this inequal. All right. So that is, then there is a constant alpha you need to decide, right? So that is the integral form solution. And then, however, how to do the numerical computation, then this integration is a bit troublesome, because this can be infinity if x is outside the domain of attraction. This will be infinity, actually. So then how you cannot do the integration to infinity. You only do the integration for finite time interval, right? Then the question is that how large this integration will be considered. Once if you do the integration in a finite time, it's very large, then you consider it's infinity. But each dynamic system, how large is infinity, that's different, okay? So, but numerically, you have to use a large finite number to represent infinity, okay? So that is, one hurdle in terms of numerically implement this solution. Numerically compute the solution, you have to ask yourself, how large is infinity? Now, this part, I use a data-driven approach. Say you can randomly choose many sample points and numerically do this computation. So that's before online, it's offline. Before you actually, that's offline computation. You just generate a lot of data and you do the computation in finite time. And then you see that that's one example. All this data, finite value is around here below 60. Then all the large number, either below 60 or your value will be beyond 200. So that gives you the idea that probability-wise, your stable trajectories are mostly, okay, has this value less than 60. And then, you're outside this one, there's a gap, okay? So this gap actually does not guarantee these are unstable, but the probability, so basically that gives you one, I would say it's one component of stability region, okay? So that represent a component or a probability rise is a represented area of domain abstraction. So anything beyond 200, there's a clear gap here, then I would consider it to be infinity. So I choose M is anywhere in between, and I choose large enough. For example, I can choose 200. Okay, so that's one way to check M, and you may still drop some, something happen to be very large, but then it's still finite. But however, it says that the probability is very low. Randomly you don't see it, right? So those are very special stable trajectory, and typically those are not robust. They are very close to boundary already. So you may consider those unstable already. So there's a numerical. That's typical in numerical. You don't get 100% exactly. So here is the concept of boundary layer, right? So in numerical computation, you never get exactly hit the boundary domain traction. You just get close enough. You think, the computer has finite digit, right? So it has a machine precision. You just get close enough, right? So then another thing I need to decide. So one thing to decide how large is infinity, So then another thing to decide, what is this alpha? That alpha actually scales your numerical range. So how to choose alpha? Basically, that's based on how thin this boundary layer. If you get into the boundary layer, numerically, I consider it's unstable already, right? How to define the boundary layer? Because you never numerically hit this boundary exactly. So you want a little recursion here. So how to define that? Well, look at the hyperbolic tangent function. It goes from 0 to 1. If, for example, if you choose 20, hyperbolic tangent of 20, it's very, very close to 1. The difference is less than 10 to the negative 16. So basically, it's getting into the range of machine precision. So I would say, okay, if this number, the total number is 20, I consider to be, you hit the boundary already. It's 1 already, right? If that's an assumption, then what is infinity? Infinity is M, right? So then I choose alpha is 20 over M. That means if my integration, the I value, so the I value, so this graph is called the I value plot, right? If my I value is M, then I consider, right, from the I value plot, I consider it's unstable. That means I consider it's within this boundary layer of domain abstraction, okay? So I can use this one. But you can choose different definition of your boundary, okay? So I've been using 20 because this is really close already numerically. So that's but you can choose something more conservative, say, hyperbolic tangent, 10, for example, right? So that's your choice. But anyway, so that's the two parameters you need to choose. One is m representing infinity for the air value, and one is this alpha to define the boundary layer. Once you choose them, now here is the algorithm. You need another parameter, say the integration. If it converge, then basically if your integration values stop to drop, right, at a certain rate, then you consider stabilized. Then this one tells me, so if the value doesn't change for a certain time interval, it doesn't change larger than delta, then consider the integration stabilized. Rather than do the solve it and integrate it, I just use this augmented system. So this is the original system, but then I add another system. So if you solve this one, then z is the integration of w. That's the I value. Okay, so just solve this one along small. So this algorithm, I call it algorithm one. This algorithm one actually need a ODE solver. Then you solve this ODE. Okay, so this then along small intervals, and then there are two cases. Either at a certain time moment, your integration or z is the I value actually is larger than m, then you stop. You consider it's infinite already. Or if this the difference, this rate of change is dropped below delta, I say okay, stabilized, right? It's kind of a similar to optimization algorithm. When the gradient is small enough, then I consider it converges, right? So that's like that, and then you define your v of x. So that's one algorithm consider to compute the v of x. Well, of course, obviously, this is a part that can be time consuming because you're using ODE solvers. But for low dimensional problems, ODE solvers these days is just so efficient. You can compute them very fast. So for those kind of problem, then for example, I use a van der Pol equation as an example because this one numerically I can find the boundary domain of traction. Using backward integration, you can find the boundary. And then so for this example, it's two-dimensional, so ODE solver is quite efficient. So now I just use algorithm one, and then so this is the parameters I choose, and I show you the air value already. So among 3,000 random points, that there is a clear gap between 60 and 200. So I choose m to be 200 that represent infinity, and then so 20 defines the boundary layer of domain of traction. And then this is, I know that the equilibrium point is 0, so I choose this W obviously satisfies all the assumption. This simple function. Now, based on that, then you can compute the air value, then compute the V. And then once so now you can program the algorithm one, this in MATLAB, and then actually, so then I can compute the V function. Remember that if V value get closer and closer to 1, you're getting closer and closer to the boundary of domain traction. So here I show you a few of these level curves, right? From 0.7, 0.9, 0.99, you get closer and closer to the true boundary of domain of traction. So that is algorithm one, based on so the parameters determined based on data driven, but otherwise it's a solution of the Zubovs equation that based on an ODE solver. And once again, when this goes to high dimension, this one is not too bad. You can compute more than 30 hertz per second. So that's not super fast, but I mean, depend on how fast you want, so that's, but I mean, I'm using this is relatively old. This is probably a 5 years old laptop. That's, that's what I'm doing here. So that's anyway, it depends on how fast you want the computation is. And then, for simulation like this is doable. Okay, but of course it's not ideal because obviously if you go to high dimension, this method will not work, right? Now that if how about the dimension goes high, then I propose deep learning. I say, okay, I have algorithm one. Algorithm one may be not fast enough for your application when dimension goes to 5, 10, 20, right? However, maybe it's still fast enough to generate data offline. Then you train a neural network. Once you train a neural network, then evaluation of a neural network is super fast these days. And there are even hardware doing the computation. So then it will be very fast when you really do the online computation. So the idea of deep learning, one way to interpret, I like it, is that you have a total computational load for a problem, right? Now the deep learning is that you generate the data and you do the training. That's time consuming, but that's offline computation. So you shuffle all the computation from online to offline. Now, once you train the neural network, you train your solution, then the online computation, when you really apply this function, that is fast, right? So you shuffle the computation load from online to offline, right? So that is that's a part about the machine learning I like. Of course, machine learning has many different properties. That's one of them I think is quite interesting to me. So the idea is that you have layers of neurons, and then you train them. How to train them? You use algorithm one at the Inequal form solution to generate data value at random points in a set of your interests. Say I'm interested in my system behavior, stability behavior within a bounded set. Then I choose random points, and then I can use algorithm one to generate the value. I use them as truths, right? So then I generate the validation data. So this training not only gave you a neural network, you can generate data to validate that because of algorithm one. Okay, so that's nice. A lot. That at least you can empirically validate the solution's accuracy, and then the loss function is quite standard. Okay, it's just found the error square error of your neural network, and means neural network approximation, and the optimal function value found. Then you minimize this one by finding the weight. The weight actually are the parameters inside these neurons, right? So this is a fairly, vanilla type of a straightforward supervised learning. The only thing is that I have algorithm one, and if the dimension is not extremely high, this algorithm one is still good enough to generate data. So that provides the possibility of using supervised learning and also validate the error, right? Now here's a question. How many neurons do you need? Remember at the beginning, I talked about the cursive dimensionality, right? So the number of neurons is one way to measure the complexity, right? So you claim, I claim that this kind of thing, in general, if you use a brute force approximation method for high dimensional problems using conventional numerical method, it suffers cursive dimensionality. How do you know that machine learning does not suffer cursive dimensionality? If the number of neurons you need to approximate the function increase exponentially with dimension, then this deep learning does not work, okay, beyond the 4 or 5 dimension, right? So that's the problem is still there. It's deep learning is not, why deep learning is the magic, to mitigate the cursive dimensionality. So that's a big question here. If you check the proof of these like a universal approximation theorem of a neural network, these theorems, most of them does not give you the number of neurons. Some of them gave you, if you use only one layer, then it can still, the number of neurons can still increase exponentially, right? So obviously these layers, everything, matters. Now here, why I want to do deep learning, I think deep learning is hopeful, at least, it's hopeful to mitigate the cursive dimensionality. Here is a claim, which I'll talk, I'll show you using example later. This claim, we proved with Qigong. We have joined paper a few months ago in SciComm, published there. Basically, we proved one fact is that if you're complicated problem has a compositional structure. For example, you have a dynamic system. The right-hand side of the ODE has a compositional structure. So basically, the structure is the following type of thing. The dimension of the system can be high, but it is a composition function of low-dimensional functions. Okay, if that's the case, then we can prove that the deep neural network solution has a polynomial upper bound of complexity. The complexity has a polynomial upper bound, not exponential. Okay, so that's what we prove. But that's for dynamic system. Does that apply to Lyapunov function? I will show you that in many cases it does. Okay, so let me use. So this is kind of abstract description. Let's talk about an example to see what I'm talking about here. So this is a simplified New England power grid system, and we consolidate in this simplified model there are many generators in this power system, right? So, but they are consolidated into 10 big generators, basically into 9 big generators, and the 10th generator represent because this power grid is connected to nearby power grid, right? So these power grid input energy into the system, so it's kind of modeled by a 10th generator. So in this, even if it's simplified, it has 10 generators, and each generator has 2 state variables: the phase angle and the frequency. Okay, so you totally have 20 state. The state space dimension is 20. All right, then that's ODE. So this problem, so obviously the dimension is relatively high, although it's not extremely high in real life application, but at least you know that it's quite challenging. Cursive dimensionality definitely is a problem. It's a huge problem here if you don't do it right. Okay, so the 20 dimension state space. However, here what I mean by compositional structure, that's a paper I was talking about in the in SciComm, and then this is a claim I talk about. Now, what does that mean? If you look at this high dimensional problem, you look into the function. This function has a clear, simple compositional structure. You see the nonlinear function, there are linear nodes. These differences are linear. These phase angle difference are linear. It turns out that we can prove that linear nodes do not actually increase the complexity of your solution. So that's okay. You only worry about the nonlinear function here. It's just sine cosine with one input. Okay, so the overall dimension, it is 2 times m. M is the number of generator, right? You have 10 generator, you have 20 dimension. You have 100 generator, you have a 200 dimension, right? So depending on how much generator you count into the power system, it can be from tens to thousands of state variables. So depending on how much detail you include in your power system model. And then, however, the local dimension of each node are all 1. It's very low dimension, right? So this actually, then this is a type of, basically all the engineering models I see so far, they have this kind of structure. If you go to their compositional structure, you find that they all consist of low dimensional input. In fact, Kolmogorov and Arnold proved the theorem. Kolmogorov-Arnold representation theorem says that any continuous function can be read into a 2-layer composition, and each layer has the nonlinear part of the composition has only single input. Okay, the linear part can be high dimension, but the nonlinear part has only single input. So this is not just a happen to be this way. Actually, Arnold and Kolmogorov proved that this in general is true. But of course, how to find those composition functions is a different thing. Okay, but the existence is there. Okay, so anyway, so that theoretically is very interesting. All right, but at least it tells me that there's hope. The problem looks complicated, high dimension, but actually, if you look into the details, it's not. Then actually, it's true. Using the theorem in the SciComm paper, and we can prove the following: for the power system model, we can prove that the Zubovs equation, the integral form of Zubovs equation, can be approximated by a deep neural network. And its error is bound above by a function where m is number of generators and n is number of neurons. You see that all depend on as a polynomial function. Or in other words, there's no exponential. It does not suffer the cursive dimensionality in the sense of exponential growth. Okay, so well, this is the error, and then if you bound the error, then this n will depend on m as a polynomial. But of course, you see that's cubic polynomial. So that means that this is the n is still big. You know, when you talk about the cubic or 6th order polynomial, this it's just n is still very big. I'm not saying this is easy now. Okay, it's still extremely difficult, but at least the theorem says that it's not exponential, like other conventional numerical method, if you want to use this integral form of Zubov's solution of Zubov's equation. So that's hopeful. The bad news is that I cannot tell. So that's a typical mathematician's talk, right? You can see that. I can show you the existence of neural network, but I cannot tell you how to find it, okay? But at least it's hopeful, okay? So it gave us a real hope that I know there is a not, you know, something exists here. It's a complex, you know, it is a polynomial complexity. Anyway, so I start to generate data. Before that, remember, I need a W function. By the way, for this power system, actually, the stable invariant set is not bounded. It's a set, contains infinite many equilibrium points, and I do not know. You gave me a initial condition. I do not know a priori which equilibrium point it will approach to. All right. So for this kind of problem, typically we define W in this way. You know, that's the right-hand side of ODE. Then F will be equal to 0. W will be 0 when when X is any equilibrium point in the set. Okay, and so then I choose a domain, you know, of interest within this domain or range. I generate, you know, about 28,000 sample points. Once again, I see a clear gap about, you know, between 135 and beyond. So I can choose M to be, you know, 250, which is, you know, typically I choose something double or triple of this value. So just make sure you're far away. And then once again, I use 20 to define the boundary layer of domain abstraction. Okay. Now once I have that, I can. This is slow. I forgot the you know what's the computational time for in average. But anyway, but that's not too bad. You can use, you know, it takes a few hours to generate 28,000 sample points, but you can generate the points, right? So I generate the training set, I generate the validation set, and then when you generate the data points, you have the the solution at the data points. So you see that's a distribution. You don't want a clear gap. You want your value V represent, you know, anywhere between 0 to 1. Actually, 1 is more important. So I like this kind of, you know, data situation where a lot of data around 1, because, you know, 1 means that you're getting close to. If you're stable, you don't worry. You know, if V is small, you don't really worry the accurate. I mean, well, numerical point of view, you still want accurate, but practically, engineer may be more concerned when you get into this region, right? So if you get close to 1, you know that you know the system becomes so kind of barely stable, right? So you have more data here. You want to get more accurate estimation here. That's fine. But anyway, so you take a look at the distribution of your data. Looks nice, and then I start to train the neural network. I used a 16 hidden layer and 40 neuron each layer. So is this the neural network that I claimed in my theorem? Remember, I proved the theorem there exists a neural network. The complexity is a polynomial upper bound. Well, this one actually in the proof requires some kind of this neural network has some kind of a structure in it. But how to find that, I don't know. So this one maybe not the neural network I talk about. So that's the frustrating part. I proved that there exists a nice neural network, but when I train it, I don't know if this is the one I proved in the theorem. But at least this one seems to work fine. So this is a 16/40 neural network, and I use hyperbolic tangent. Well, that's another interesting. Remember that the I value function, that's then the V of X is a hyperbolic tangent function, the final, right? And hyperbolic tangent happen to be a widely used neuron in neural network, right? So I just use a hyperbolic tangent. So you already have one neuron there already in your V function, right? Then you just learn the other layers to represent the kind of representing the I value actually. So I use hyperbolic tangents naturally to represent this Lyapunov function. It's RMSE, the average error in some sense, you can consider in that way. It's at the level 10 to the -3. It's not super accurate, and which is not surprising because this is relative to the error upper bound I proved earlier. It's it gets into this cubic polynomial. So that can be still large. To beat that one, you need a lot of neuron to beat that one still. So. But anyway, if you go beyond, use too many neurons, and training will be so slow. So once again, I just use my laptop and then do the training for this one. So that's not bad. I mean, I think it's a typical, based on my experience, the neural network approximation function or regression solution. They are not numerically highly accurate like machine precision or 10 to the -8, 10 to the -10. We don't often get into there for high dimensional problem. If you use a supercomputer, we'll get there with a very large neural network. Maybe I never tried it before, but however, given it's 20-dimensional problem, I can say it's still highly nonlinear, definitely highly coupled nonlinear system. You use a 16/40 neural network to approximate is a Lyapunov function, and can tell you the boundary of domain abstraction. So I think it's a nice combination. It's kind of sweet point of high dimension and also the boundary domain of abstraction. You can face all the three challenges in a combination wise. I think it's a good solution. So I think that's the main part of the talk. So basically, to summarize, I already talk about this. Basically, I propose two solutions of Zubovs equation. One is the integral form solution based on data-driven to determine parameters in it, and I also proposed a numerical method use supervised learning. Okay, so the power system is one example, which is not low dimension. 20 dimension is it's not low, it's pretty high, you can say that. And then so we proved the existence of a polynomial complexity upper bound, but anyway, we trained a neural network, showed that you can approximate the Lyapunov function with a acceptable accuracy, I think, and the neural network is not complex and not too complicated. So that's the summary. And the future work, I think right now, I'm working with Kai Sun and his team on possibly, improve the neural network by designing a good neural network architecture based on the compositional structure, rather than just dense connections between layers. Maybe you select the connections wisely or smartly so that you can reduce the complexity and or boost the accuracy. These are related to each other. So I think that's something that will be very interesting. That would link to that existence theorem in the design of a neural network. That's something I'm also working with Qigong in UC Santa Cruz, doing other problems, trying similar idea to design neural network architecture smart in a smart way. So that's what we're trying to work. It's challenging, but I think it's very exciting to try that idea. That's for future work. Okay, thank you for your attention. And I think that's all for my talk today.
All right, thank you very much. Thank you. Any questions? Comments? Yeah, please go ahead. You can unmute yourself. Yeah.
Okay. All right. So I see Hongjin Wu has a question. So in many application scenarios, we may also interact in how the Bayesian geometric changes with system parameters. Thus, have you think of user method to see how the Bayesian change? Okay. Yeah, that's a very interesting question. That's true. When parameter change, the Bayesian actually change. Now, for low dimension, once again, the cursive dimensionality comes in here. For low dimension, you can almost visualize, and then using the integral form solution, that probably okay. For the short solution answer is that no, I haven't considered that problem yet. It's a very interesting question, but numerically, you can show it for low dimension using the integral form solution, or you can train a neural network if you want to speed up computation, right? So that's very interesting. For high dimension, that's hard because you see that every function v, you need to do a training. So once you change, then I would say there are two things you can try. That's, if I do it, I would think of two things on top of my head right now, okay? One is, but I do have something, other problem have similar issue you mentioned when I talk about, modeling of a PDE, I have similar problems. I have one initial condition, but then I have uncertainty, a boundary condition. Then I have to figure out, right? So one thing, if your uncertainty is structured by some parameter, so then you can, when you do the training, when you generate data, you integrate, you include these parameters of uncertainty into your data set, okay? Then it depends on that, it will increase dimension, okay? So but at least, you can take that into consideration. Then you train the neural network, okay? So that is something I did for model simplification using machine learning before. It seems to, once again, for moderate dimension is, if you don't have thousands of parameters, you have, 5, 6, I tried, 5, 6 parameters plus a space dimension, tens of space dimension, it seems to work. So that's one thing. Another thing is indirectly is this probably, you consider so-called controllability. So you have one V, and then you see how this system behaves, controllability, if it's strongly controllable, along the boundary, then you probably feel that you can, or it's just control system, right? So, but maybe it's irrelevant. Here you're just talking about dynamic system. But anyway, so I haven't tried that yet, but I think if you include the data set, include the parameters of uncertainty, that will be interesting. But I don't have example for that. Yeah, good question.
Yeah, thank you. Do you want to? So there's not someone you can unmute yourself there too.
Yeah, can you hear me?
Yes.
Oh, hey, Jiaqin. Nice to see you.
Wei. Yeah, nice to see you. And for me, yeah, very nice talk. I have one questions for, so for the in your second example for the power grid.
Okay.
How to say? I mean, you show the regression error and the plot. So I'm interested, what will be the potential application for getting the domain of attraction information in this kind of systems. Later you mentioned that you are considering whether you can design better network to get better performance. So I'm curious, like, are you interested in getting like a lower regression error, or that the domain of detection will be used to some other applications so you can check different networks performance?
Yeah, so if you, I think you have two questions here. One is that what is you know, the potential application of finding the boundary domain abstraction, and another one is how to, you know, how this can be useful if you can simplify, you know, design the architecture.
No, I guess my second question is related to the first question. So you said that you want to see whether can utilize the compositional structure. So I mean, then you have different networks. So how to compare them? Only checking whether they have lower prediction error, or it is related to further applications.
I see. Okay. All right. For the first question, you know, how this is the finding the boundary domain abstraction, like for power system, actually is a long time open problem. That's why we have a blackout. You know, especially large scale cascading failure. You know, because we thought it's stable, but it's not. Okay, then things can go wrong very quickly, right? So predicting how close you are to the boundary of domain abstraction is still an open problem. You know, even this one use a simple you know, model. So that is then there are other things like you know, when you design the you know, what try to find you have many UAVs flying right in a small region. You want to one way to check the, you know, if you have a potential you know, collision, then you want to find the you know, the boundary of your reachability is related, right? This kind of thing. So but anyway, so for the second question, yeah, it's I think right now in my mind, I would say if I want to design architecture based on composition structure, I want to see one of the two things, or maybe both. One is that I want to see the accuracy increase using the same complexity. Here, the complexity maybe is not the number of neuron now. It will be number of neuron and the number of parameters. Basically, hopefully they will be sparse. That's what I hope. So that's one thing. And then because supervised learning, if you have the data set to validate, so you can check the accuracy. So that's obvious one measure. Then another thing will check, say, if given the same accuracy, you know, how many parameters I need. Hopefully it is lower than the dense type of neural network. But that's what I hope. But I know that's right now it's just a hope because I haven't tried this yet. That's there are a couple of examples we're trying, but haven't have a solid result yet. So yeah.
Yeah, maybe I can clarify your answer to the first question. So can I think that we hope the power grid systems always, the state of the power grid systems is always in the domain of abstraction so that it can run stably. So getting the solution can give us an indicator whether it is in the region or not, so that we can.
Yeah, this is okay. Yeah, yes or no. This is related to the first question now. Because you know, if you get, you know, we cannot guarantee you'll stay in it because there are uncertainty. So you have one model, then their parameters change, right? So that's why it will push you when parameter change. It may push you outside the domain of abstraction. So then once you get close, then the power utility company or the power control, they will decide to what to do. So they are going to change. In the extreme case, they even shut off part of the grid, so you have a power outage for so that they can stabilize the system, right? Because the balance and they have to balance the load and output. So you see that there are all these parameters. You have artificial control not artificial, you have real, control that change the parameters in the system. Then you have uncertainties that change the parameter in the system. So in my example here, I haven't considered those in. So once those are in, then it will be, then I can say, okay, this will tell you how to always stay in the domain of traction, because it included your control parameters already. That's a much harder problem still. But this is but let's hope if you can integrate these uncertainties or the variables in the system, then you can say more about staying. When you say staying in domain of traction, you already have some kind of control ideas in it. Yeah.
I see. Okay, thank you very much. That's very helpful.
Okay, thank you.
Other questions or comments? Yeah, okay, seems there are no further questions.
Okay, I know you guys must be hungry. All right, it's a dinner time. All right.
Yeah, exactly.
Yeah.
Yeah, thanks again for the nice talk. Yeah, thank you very much.
Thank you. It's always a pleasure.
Thank you.
Yeah.
Yeah,
All right.
thanks everyone. Thanks, bye-bye. Take care. Bye-bye.
Okay, bye-bye. Yeah.